The next speaker is New Concepts in the Theoretical Description of Solute Adsorption from Dilute Solutions of Solids by M. Jaron Knight, Institute of Materials Research, McMaster University, Ontario, Canada. Dr. Jaron.
I will talk to you.
Huh? No, here's one. You don't want this?
Okay,
No? Okay.
The present, my address is Georgetown University, Washington, D.C. and permanent.
Yeah, what happened here?
Because I moved from Canada to
Okay.
Georgetown University, and permanent address Madame Curie University, Lublin, Poland. And there is a great interest in adsorption, solute adsorption from dilute solution, especially to describe adsorption of organic substances from dilute water solution and activated carbon, and to develop theories of liquid-solid chromatography with mixed mobile phases. I would like to give a short information about problems which are interesting for us in the last time. The first is models of solute distribution between surface and bulk phases, and I have some reference paper which has been published in Journal Chromatography, and in this paper we discuss models, partition model and displacement model of solute distribution between surface and bulk phases. Next, the concept of energetic heterogeneity in solute adsorption and concept of structural heterogeneity and relationship between these two descriptions. And quite new, the concept of surface activity coefficients, which involving non-ideality of the surface phase generated by adsorbent heterogeneity. And of course, application of a theoretical description for single solute adsorption for predicting multi-solute adsorption data. Shortly about adsorbent heterogeneity, and in this description we use in majority case energy distribution function, key function of adsorption, key function of E. E is adsorption energy of solute with respect to solvent. It means that it is difference of adsorption energy of solute and solvent. And we can evaluate from absorption data this function. However, we receive information about global adsorbent heterogeneity. I think about surface heterogeneity and structural heterogeneity. Recently, some scientists propose to use another distribution function which are dependent from structural parameter B in the Dubin-Raduszkiewicz equation or microbore dimension X. More general description is using energy distribution function is equation 1. This is equation known and presented was yesterday. That is global absorption isotope, local absorption isotope, and energy distribution function. And we can solve this equation for Langmuir type local absorption isotopes, and the general solution of this equation is given by equation 4 or by equation 5. Equation 4 may be understood as a generalized form of Langmuir type equation and contain parameter Langmuir constants and parameter m and n describing shape of energy distribution function. And this equation corresponds to different type of simple energy distribution. One of them is symmetrical or asymmetrical function. Another equation is to be Dubin-Raduszkiewicz type, more generally Asapov equation, and this equation corresponds also to similar energy distribution function. The recent studies show that in wide concentration region, the two equations are quite equivalent, that it doesn't matter which equation you use. And I recommend the equation 4 because on the basis of integral equation, this equation contains quite exact foundation. The equation 5 may be understood as approximate equation only. And this is a sample of application of this equation to description of adsorption visualization from diluted water solution on activated carbon. And it represents quite good experimental data. And this same data is by using Dubin-Raduszkiewicz equation. And another description is when we use conception of structural heterogeneity. This equation 6, contains as local adsorption isotope Dubin-Raduszkiewicz equation. It means that we postulate that Dubin-Raduszkiewicz equation describes solute adsorption on uniform microporous system. And it is of course possible to solve equation 6 for example, gamma type and distribution function, and we obtain a simpler solution like equation 10. This equation also gives interesting good representation of experimental data. And what is interesting, that we can correlate energy distribution function and this micropore distribution function. It is related. One is energy distribution function. Here is the distribution function of micropore dimension, structural parameter of micropore dimension, and we can recalculate from energy distribution function the micropore distribution, and vice versa. If we know the micropore distribution, we can calculate energy distribution function. Another approach is to use conception of activity coefficients. In this case, we assume that activity coefficient in the bulk phase, of course, is dependent only from interaction between molecules. However, activity coefficient in the surface phase is dependent from interaction between solute and solvent molecules, and is dependent also from non-ideality of surface solution generated by adsorbent heterogeneity. And in this case, we can use the same equation which I used to homogeneous surface. However, we only modify the conception of surface activity coefficients. And of course, this approach is quite useful to define displacement model or to define partition model, which was used to develop the liquid solid chromatography. I think another interesting case is application of single solid adsorption data for prediction adsorption from multi-solid phase. In this case, adsorption is described by multifold integral equation, and we can use two ways for develop two ways for solve this integral equation. One, where we have energy distribution function identical shape, only shifted on energy axis. Another, when we have different shape. And we assume that area under the energy distribution function for one solute is equal to area under second distribution function. And we resolve the function, distribution function as function of energy, and we can transfer a multifold integral equation to singular integral equation. This method is quite new, and now preparing the paper for publication. And I would like only to show how we can use Harris correlation for single solute adsorption data and desolute adsorption data, where we use this simple method, or in case where energy distribution function has the same shape and are only shifted on the energy axis. Here I have correlation according to the Raduszkiewicz equation for single solute adsorption data for different solutes from water solution on activated carbon. Here is correlation according to generalized Lewin type equation for desolute adsorption data. If we calculate parameters for one straight line and for second straight line, it means that parameters from single solute adsorption data may be used to predict multi-solute adsorption. And especially the extension of this method, especially where we have different energy distribution function, is quite interesting, because in many cases, when the solutes have different chemical properties, we should use this extended method. I would like to tell that this problem solute adsorption is quite difficult. It is dependent. From many factors, and I think that many questions open, like problem irreversible adsorption and problem of dissociation of solute in the water solution especially, and another. And recently we sent to publication a review on adsorption of organic solutes from diluted solution on solids to surface and colloid science. I think that will be appear in volume 14. And in this review, of course, we also discuss very known approach like potential theory to solute adsorption developed by Professor Manes and another, and solute-phobic theory in the solute adsorption. Thank you very much.
Okay, thank you, Dr. Johnson. The title of the next paper is Adsorption of Aromatic Compounds from Solution on Solid Surfaces by Altikov and Altikov, Institute of Physical Chemistry, Moscow. This talk will be presented by Professor Lardov. It's like this. Make sure this is no, the other one. Yeah. And the pointer is.
There is two reports in our programs which presented by Elter. He asked me to present it here. These reports are very large, and because I didn't want to examine your patience of my bad English. I make one short report of them, and now I try to present it. The HPLC finds an very interesting application not only in the analysis of separation of mixtures, components, but also in the physical chemical studies such as the determination of Henry's constants and isotherms of adsorption from solutions. In present work, a possibility of determining the adsorption isotherms, Henry's constant, and activity coefficient in adsorption solution by the evaluation liquid chromatography method is demonstrated for adsorption of anisole and benzaldehyde from solutions in N-heptane and hydroxylated and polyethylene oxidate modified surface of macroporous silica. This slide demonstrates the method. That is chromatography peaks which we find when we use different size of sample which we introduced into chromatography column. The maximum of the peak is the characteristic of chromatography of adsorption system, and we can use it to determine the adsorption. This at this slide we show we see the equations by which we can calculate the adsorption. That is adsorption, that is the retention volume, concentration, and that quantity may be calculated of this equation, and this equation where LH is the position of the peak and LO is the position of the peak of unadsorbed component. This slide shows the initial parts of the adsorption isotherm of benzaldehyde in the region of low equilibrium concentration obtained by chromatographic and this is and by statistical method. In this region of concentration, the benzaldehyde adsorption value does not exceed 0.0002, and adsorption isotherms are linear. As is seen from this slide, for the silica hydroxylated surface, the benzaldehyde adsorption isotherm obtained chromatographically is below the adsorption isotherm obtained by the static method due to the non-equilibrium character of the chromatographic process in the case of benzaldehyde adsorption. The isotherms of anisole adsorption from solution is solution in N-heptane obtained by the chromatography methods, and statistical methods are in the next slide. we have the initial part of isotherm, which became but by chromatography method. Here, there are the points which became thus by chromatographic methods, and the point which became by statical method. And here is the parts of isotherms by more large concentrations. The adsorption isotherm in this range is also linear, and as you see, the adsorption measured by chromatographic and statical methods is the same. At this slide, we show the isotherms of anisole and benzaldehyde, which became on CO2, on silica gel, and on silica gel modified by polyethylene hydroxide, polyethylene oxide. As in previous case, the adsorption benzaldehyde on the silica gel is lower when we measure it by chromatography method, and coincide in the case of modified silica gel. Here are equation which was used to calculate the thermodynamic characteristic of adsorption. That is the constant of equilibrium, and that is Henry constant. C is concentration, gamma is coefficient of activity, gamma is adsorption, mu is chemical potential. Here indicated equation which they used to calculate the constant of equilibrium and the activity coefficient. When used the activity coefficient, then they used some function which is connected with ideal adsorption. The concentration in the adsorption phase they calculate by usual method, where AM is adsorption of the first component at the concentration of at the mole fraction of 1. Beta is the relation of the M1 or AM1 to the AM2, and that is adsorption. So from chromatographic date, Henry constant is related with the molecular volume of the component, and Henry constant is when we calculate it with mole fraction with the same with this equation. Here we see the values of constant, equilibrium constant and Henry constant for substances under investigation. Anisole, benzyl, benzaldehyde. M is date for modified adsorbent, and H is for non-modified adsorbent. You see that
what is the modification?
Modification, polyethylene oxide. You see that Henry constant, which we find with chromatographic date and we calculate from the equilibrium statical method date, is equal to 1, but to the system benzyl aldehyde it is only 0.5. It indicates that in this system we have not equilibrium. At this slide, I indicated the activity coefficient in the surface phase for modified, for benzaldehyde, for modified silica gel, non-modified silica gel, and this is to the anisole, also to modified and to non-modified silica gel. Here I indicated some thermodynamical functions to investigated system. That is free energy of adsorption, that is enthalpy of adsorption and entropy of adsorption. No, I didn't want to comment this because you see this quantity. We may only indicate that the benzaldehyde has the more value of enthalpy of adsorption. That's all. Yes. So you see that method of liquid chromatography may give us a new possibility to investigate adsorption by very little, by very small concentration. And we may use this method to measure adsorption and to receive some thermodynamical data. Thank you very much.
Would you like to take any questions? I can imagine how difficult it is to present someone else's paper in a foreign language.
In a foreign language. Just one question I'd like to ask you. What do you think about the possibility in the future of changing the nature of the solvent by attempting to reduce the polarizability of the solvent? This would present experimental difficulties, but it would be quite an interesting thing to attempt to do. Reduce polarizability by working at a lower temperature. Do you think that's possible? Using chromatographic measurements at lower temperature?
We may use it at every temperature.
Well, that's the question about
If our solvent not freeze.
Yes. Yes, you'd have to use a different solvent, of course,
Yes.
obviously.
Yes, we may use a different solvent and we may
Reducing the competition.
the mixture
Yes.
solvent.
That's right.
Also.
Yes.
We may, to measure with this method, many components solution, polycomponent solution. Because if we use polycomponent solvent and introduce some solute, we have a peak, and we can calculate the absorption of this component from this mixture.
Yes. But at the moment, you have to be prepared to accept quite a high intrinsic adsorption by the solvent at the present time. Competition by the solvent is unavoidable.
Yes, competition will be, but if your solute absorbs better,
Yes.
it came out of town at the larger, more, the larger
Right, concentration.
But if it absorbs further,
Yes.
then the solute,
Solvent.
then it came of the town before
Yes.
this time.
We have another question.
Well, it is only a comment. In the description, the competition is included because the Gibbs dividing plane is placed where the sum of the surface concentrations is 0, so that gamma heptane and gamma anisole plus gamma anisole is equal to 0.
Yeah.
Yes? So that this is a reduced isotherm with a U shape, so that it immediately describes the competition. Now, what I would like to ask to
Can I just interrupt you?
Helmikov,
Can I just interrupt you?
Yeah.
Although it's taken care of, I appreciate that. But I think that that is so in the analysis and treatment of the data, of course, you're right. But it would be of interest to attempt to change the relative adsorptions of the two components. And to do that, at the moment, you are restricted by the nature of the solvent and the working conditions. So in other words, you have to change working conditions.
You can
the
use
second component is the solvent.
Yes, I appreciate it.
Heptane is the solvent. want to measure, it is
But
a
whether you like it or
competition.
not, there is competition process.
Yes.
What I'm suggesting is that you change the
Yes.
system.
Yes.
You change the system
Yes.
in order to separate these two, the components, the intrinsic adsorption affinity, if you like, to separate them to a greater extent than you can.
You will change the extent of competition.
That's right. That's right.
Anisole plus gamma, anisole is equal 0.
Yeah.
Yes? So that this is a reduced isotherm, because a U shape, so that it immediately describes the competition. Now, what I would like to ask to
Can I just interrupt you? Can I just interrupt you?
Yeah.
Although it's taken care of, I appreciate that. But I think that that is so in the analysis and treatment of the data, of course, you're right. But it would be of interest to attempt to change the relative adsorptions of the two components. And to do that, at the moment, you are restricted by the nature of the solvent and the working conditions. So in other words, you have to change the working conditions.
You can
The
use
second component is the solvent.
Yes, I appreciate it.
Heptane is the solvent.
Yes, but
And you want to measure, it is a
whether you like it or
competition.
not, there is competition process.
Yes.
What I'm suggesting is that you change the
You
system.
change
You change the system in order to separate these two, the components, the intrinsic adsorption affinity, if you like, to separate them to a greater extent than you can.
you will change the extent of competition.
That's right. That's right. That's what I'm suggesting.
Then you may have a chance that your solute and your solvent will retain the same time in the solvent.
I think right.
It will be the zero absorption in the Gibbs sense, in the sense of the Gibbs.
Go on.
Okay, as I will comment this comment, because this experimental data presenting activity coefficients for silica, non-modified silica gel modified, gives a very nice confirmation in my talk about the solid distribution between two phases. When we have non-modified silica gels, the activity coefficient is quite close to unity in this region. It means that it's displacement model, competition model. In the case when we have bonded modified silica gel, it may suggest that some model that solute is distributed according to partition model by the different interaction between the surface phase and in the bulk phase.
What we'd like to do, in fact, is experiment the system. You don't really have to go to another solvent. That's because if you are willing to move out of the Henry's law group and look at deviation from that, but then, in fact, what you will be doing is probing the solvent structure near the surface, so that I don't know what the difficulties are in doing that, but essentially the Henry's law concept is looking at all the configurations and averaging them up right there at the surface with the solvent and into the solvent. The deviation from that, and it probably will be quite significant, easy to measure, I think, will appear as how those two solute molecules are disturbing the solvent structure. And so effectively, it's like changing the solvent, but going in very slightly, very softly into that effect. So I think that, in fact, would probably be the way to do that.
This is another problem orientation.
I think this effect will broaden the peak for, yes, but in this work we used the retention time or retention volume of the peak, of the maximum of the peak. And we know that the maximum peak goes came out of the column independ on the broadening effects. It depends only on the equilibrium in this system. And you saw here that benzaldehyde, which interact very high with surface of silica gel, is not in equilibrium at this rate.
That's why,
presumably,
that's why you get better agreement with the low energy surface than you do with the original silica, hydroxide silica.
you have to use the slow. See?
Any more questions? Thank you, Professor.
Questions I would put to the author because...
Well, any more discussion? Because the discussion was very good. I have one quick announcement. The banquet tonight is at the Student Center, second floor, 6:30. That was changed? The location was changed? Oh, then why am I making the announcement?
But a number of people were concerned and it didn't say it.
Oh, it didn't say where it was. Okay, Student Center, 6:30. Don't miss it.
Yes, buses will run.
Yeah, because we haven't got a great...
And that concludes this afternoon's session. Thank you.